Okay. Just for the purposes of this video, so that I can share that for the other people, the students that I have, like that are not speaking in Latvian, I will speak in English. And yeah, so I shared the template for today's work, and the paper that we're going to look at, and there's going to be also another variation, very interesting variation of the what is known as a kind of state-of-the-art LSTM. So the phased LSTM, the main purpose is long event-based sequences. It's very similar, like advantages as for the transformer. As far as I know, that this kind of university group that published this work, they also have the patent for some of things that are included in this this architecture. And as I mentioned, so today we'll make a very simple LSTM, then with the peep holes, and then we'll start making the phased LSTM. And then after that, I have the idea of another variation of LSTM that I know works really well. So this is all about recurrent neural networks, right? So there are multiple ways how to display these architectures. You can have many variations of schematics. So this is one of them. And here you see that on the left side, this is actually not completely vanilla LSTM, but there is a peep holes also. So what are the peep holes? It's meant that you have some kind of projections from the C vector to the gates. Not only having, so the vanilla version is actually looking like this, where you have like the C vector is not connected with the gates. So it's just the X is connected and the H is connected with gates. This is another way how to look at these equations. But here you have the peep holes as well. And here for the phased LSTM, we also have additional gates. Additional gates K here. This is conditioned on the C, I guess, here and here with H, I think. So we'll see the equations. And the one thing that need to be seen here is that the T is also coming in. So the T is, in this case, is actually the, as I understand, the index of the timestamp, but it could also possibly be encoded in some other way. But I guess because of the formulas that they have, it would work the best if it's encoded in some kind of scalar manner. And the way how then it works is, this is the simple architecture, so with the peep holes added. So if we compare with this one, we'll first just implement the simple one, and then we'll add with the peep holes. So we see that there we have these equations here. That's actually the Hammond pairwise products coming in these positions. Also here. So in three places, here, 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 there are peep holes. If you look back here, we have one arrow here, the second, the third. So 3 peep holes, right? Then the other thing is, if you look at the architecture in another way, then you see there is an input and the T index, and the layers are actually the just the cells of these phased LSTM equations. So there could be one layer, of course, or multiple. And the main idea of phased LSTM is that you have learnable phases and shifts of the gates. So the gates are open only when you learn, when you need them open. So even with the peep hole based simple LSTM, we have vanishing gradient problems still. So if you have very, like, the long sequence would be longer than, let's say, 32 or maybe 64 inputs, then the phased, like the simple LSTM degrades quite rapidly. There are some tricks that I will maybe show next time, but in general it's not good. And for the phased LSTM, you can have thousands of time steps, no problem. It will work great. So, and the idea is that it will learn the parameter t, the parameter s, and it will simulate the effect of opening and shutting closed the gates. So you can imagine that there is just like this vector that is like the openness of the gates depending on the phase and the shift, and then the high frequency is here, the low frequency is here, for example, and yeah, and then you get the output C state. The equation for, so if you come back to this cell here, there is the K. So the K gate is calculated using these equations. So with three conditions. So here here you have one hyperparameter. That is good. That there's actually not many hyperparameters. There's just one. The R on this one, and I give the what is kind of open ratio. What is good value to start looking. And then you have the T is the index of the time step, S is learnable, the tau is learnable, then the alpha is learnable. Alpha, this is like a leaky parametric ReLU or something like that, where you if you don't hit the phase intervals, then you have not killed the gradient completely. It's hopefully it goes through with some kind of value. So this is basically that part. And then they modified only the last two lines. They add to the C vector some modification here by adding the K here, and with the H also K here and K here. So that's about it, about the architecture of the function graph. And I think, okay, this was regards, I think, to the gradient loss. Then I have some examples, quite really good ones. I mean, so if you have some different kind of sampling of some toy data sets, so if this is a uniform sampling, then there's not a big difference between different kinds of LSTMs. As soon as you have really non-uniform or like even maybe. So what is happening? Something is going. Okay. So even some kind of sampling that is really not like with the same frequency, then the phased LSTM is like so like by the magnitude better. And also some other tasks also shows significant improvement. The one way how they test all of these things is using the MNIST dataset. So you also test with other ways, but the one way is using just the visual dataset of the MNIST of the 28 by 28 pixels, and then just treating them as a long sequence. That is a little, but that's not like the best dataset, but also it's a way how to evaluate it, and we will do that today as well. So far, any questions regards to the architecture itself or the reasoning why you would want this, or everything clear? What do you like? What do you think? So let me check your faces. So no faces, but hopefully it's clear. I hope, really. So anyway, if there is any questions, something not clear, then let me know. So and let's go then to the code. So if I open this code that I had before, that I shared you. So if I post this video somewhere, I will also give the template with this one. So here we have, let me go over it. So first of all, I made this that for the GPU it would take the whole dataset, but for CPU it would take only a small part of the dataset, just for the validation purposes, so that if it works. Then the other thing is that I selected only the three classes for the letter 0, 2, and 7, and I used the MNIST dataset. You could also try to use extended MNIST. That is a little bit harder one. And also you could include more classes. So as soon as we get this 99% accuracy with these classes, then I suggest including more and more and more until we see significant degradation, so we can see the benefits of the phased LSTM. So this is there is also like so if you think about MNIST dataset, so just for most of you, like, you already know it very well, but if you just look at it a little bit, the number is actually in the middle part, always in the middle part of the image, and depending on the class, there is some kind of frequency going on. So if there's like a 1, it's always like mostly till the middle part of here. The frequency is, if you look at rows, so we can look at it in many ways. One way is that we looked at the time dimension is over y axis, so the vertical axis. And if it's like a time dimension, then we see that, first of all, like, it starts not immediately, but at some delay. And then it always kind of, the frequency is somewhere in the middle. And then at the end, again, the nothing. Or we can also look at this as a long sequence of one dimension. So we can put together each row as a long sausage. And then, again, there would be some frequency. So depending on these numbers, there should be different frequencies, and that's, I think, quite interesting. So here, if we sorry, I forgot to show you that picture. Sorry, I am really sorry about that. So if at some moment I'm talking about something and you don't see the picture, please tell me that. So again, different kind of frequencies for different kind of letters. The rows, let's say, are time dimension, or if we combine all rows together, that could be also time dimension as one dimension, or as 28 dimension. So okay, that's about the dataset. So here we also add the min-max scaler, just to make that the input features are a little bit more uniform. It could actually maybe not be necessary. Then also in this case, I use input features as 28, so that we would have 28 time steps with 28 input features. That's our dataset. Then we have train test split, of course, hopefully, yeah, it is train test split. So then we have the LSTM module, where we'll quickly code the actual LSTM equations and then add some modifications to get to the phased LSTM. Here we have the very simple model. So the model also, this is highly advisable. So from the research that I have seen, you should always have the linear projection before and after the LSTM. There, I can later show you reference. Basically, that improves the quality of the output. Also, there are some tricks that we will not use today, but there are that should be used. And here at the end, so let me quickly give you some examples what is coming in here. There is going to be the batch, comma sequence, comma features. So it actually would be, let's say, some kind of batch, comma 28, comma 28. Then after the LSTM here, so here after the LSTM call, we would get the batch sequence and the hidden size. Then we would calculate the average value over the sequence for each of the samples of the batch, and in that way we would get just the output as the batch, comma hidden size. And if we have this one, then we can easily project that to logits, softmax, and then pass to the cross entropy here. So I wrote out the cross entropy with the equation. I always like to write the loss functions with equations. That way I get a little bit more control over the way how it works. Even with the cross entropy, there are a lot of things that you can play around. So here, let's start with the LSTM. So what we have there is that we would need to have, at least in the beginning, without the peep holes, we need 2 matrices and I think bias, if I'm not mistaken, because I think it was like that. And I also, when I tested it a little bit around, it was interesting to see that initialization is very important. Actually, there is one trick with regards to forget gate that is also beneficial. So here, let's start typing. So self hidden size. Hidden size is this one. So just like for the ease of use, that we can use it also here. It's actually already written. So also like in a PyTorch, the hidden vectors, the H and C, can be skipped as well. That you can give them immediately, or you can skip them just so that for example, if you would like to roll out the sequence, for example, you have some kind of language modeling task and you would like to extend it over the so if you have different size sentences, or you would like to see what would be the next word, then you can pass in the previous hidden state and just generate the next step. Or you can, if the sequence size is already known, then basically you don't need to do that. And especially if the sequence size is the same for all input samples. So it is not always the case, but in this case it will be. So then, let's start by adding if you look at the equations, there is this weight equation for the inputs. Also, usually, like almost every time, the people define these matrices as for every gate, just like a part of that matrix. So probably it just learns the correct these dot product correlations, and that's why it works after the convergence. But of course, if somebody wants, you can split it in 4 parts, but like it usually doesn't make sense. It have the same result after the convergence if you just use one. So if you just use one matrix for the projections of the inputs, then it means that we need to have it for the 4 gates. So it's not enough that we just have the input size here and the hidden size here. Sorry, it's a little bit wrong notation. I need another parentheses here. So the input by hidden. That would be just one small matrix that would constitute to the like a projection from input to the hidden size. But in order to have 4 gates, so we would have 4 gates covered by just one dot product, then we would multiply this by 4 and also multiply this by 4. So with the gates, there are, if we look at the equations, there are the input gate for get gate, there is output gate, and there is internal this cell state update gate. So that's why we have 4 gates for LSTMs. That's here. Then let's think. So I think it's actually, let's see. I think you could leave out also without those double parentheses, but maybe you need them. So then the initialization. So usually you can initialize that by uniform. The one thing that I found out that it works much better. Actually, that is also very interesting. I think I would look up a little bit more why exactly it works so much more better. Is that if you calculate the standard deviation of that, so I see that Walter's joined as well. So I posted the template in the chat for today's workshop. I also hope that you see the code in a correct manner, because in my screen it's like in the mirror side. But so is everything visible? Okay, is everything? So maybe somebody can tell me. Okay, cool. So yeah, so uniform here. Then maybe somebody knows the answer why this works so well. It would be great to hear and understand a little bit better. So I will read myself as well about it. So if you calculate the standard deviation of the uniform, like what is the amplitude of the uniform distribution here, depending on the hidden size, like self-hidden size, and then initialize it by this manner, then rather than just from, I guess from -1 to 1, no, from 0 to 1. I guess that's because, okay, so my hypothesis is actually that's not real regarding the standard deviation, but because it's just from the 0. So I mean, we can experiment later. I think that if we just initialize it from the -1 to 1, it would also work quite well. But let's leave it with the standard deviation, as some implementations use it. But let's add also that we can try out later. Test -1 to 1. Because by default, it's actually default is 0 to 1. And I think that's why it didn't work as good. Because at 0, these functions kind of, like, for example, 10h is -1 to 1. So I mean, so that it will not be beneficial if it starts from the 0. So that is this one. Then the next one is for the hidden state, right? So this is the W, then the U. Again, exactly the same thing, just copied with a different parameter name. And the last thing that's needed is the bias, of course. So bias. Again, torch float tensor. And bias we initialize as zeros, of course. Like in most cases, it's be good. And then remembered. So for the, if I remember correctly, the optimal way how to do this would be to initialize forget gates for the for the part of the forget gates as ones. So we can, if I remember correctly, so initialize forget gate part as 1. It will be not be difficult to do, so you will see it very soon. So if you initialize it for getGate as 1, if I remember correctly, then the model in the very beginning of the training would pass everything, so it will not forget anything. So that is good thing in the very beginning, and later it will start forgetting things. So, but I think some frameworks actually don't do this by default, so it should be checked like that. So that is the initialization part. Then of course the actual execution part here. So if you don't use the torch, so if you would use, let's say, Keras or the original implementation of the PyTorch LSTM or other popular recurrent neural networks, then it would use the CUDA DNN, I think was called, where you have highly optimized this RNN function call without the for loop that is inside your own code, and they handle this on, like, they try to optimize as much as they can. But in our code we need the for loop because they are dependent on the previous states. That's why let's flip around a little bit our dimensions. So if the x right now is in the shape of batch, so the batch sequence and features, that is what we have for the x. What we want is to have the x sequence in the front, and that we can get by permute. The PyTorch have the permute function, so we can flip around the batch and sequence and get the sequence batch features. And actually, if you use the default implementation of the PyTorch, you must, I think by default it's actually the sequence is first one, so you must specify which part you want as the first one, and like you could mess up a lot of the things probably if you don't think about it. And also here for the hidden states, that is also, I think, important. Let me think. Is it important? Maybe, I think not actually. So anyway, interesting. Why did it was the so I'm not I think the hidden state for the original implementation is a little bit different, but here it will work like that. So the H out is a list here. That's fine. So cool. So let's start for xt in X sequence. So we go each step of the X and produce xt. Then we calculate the gates. So the gates, that is from the equation that I will maybe briefly show you again, so that we know the equation. Okay, this is the with the peep holes, without the peep holes, maybe so that you could see it a little bit better. So just a second, changing the so here you have the W multiplied by not multiplied but dot product by X, and the U dot product by H. So this is like split in 4 parts. So each of the parts produce the gate with the sigmoid and with the plus bias, and then you have these Hammond products and calculation of the basically the C and H state. This is without the peep holes, and that is what we'll quickly do, and then we'll add the peep holes as well. So if you go back to the code, so the gates. Maybe I will also share this video later, so if somebody's not catching up with this, or if somebody needs the code afterwards, then just let me know. So torch the matmul. So if you know that matmul is the dot product just repeated over the patch dimension, so that is very useful. So xt, then the repeat. So yeah, x right now is actually, so if you look at the shape of x, it is right now here at this stage it's batch comma features, but we actually need batch comma features times 4 like that. That's why we will repeat it. So we'll repeat it over the dimension of the features. So the batch dimension stays the same, 4 times the features dimension. Then the self with the weights. Then plus, oh sorry, it's on the bottom part. So plus this one. So with the hidden state now, the hidden state is something that will be changed by every iteration. So we just, let's say, have H here from the beginning of the H in the beginning is zeros. The other thing that we can just add here, there are a lot of cool things that you can do. I will explain them maybe next time as well. But here what you can do is to do learnable H0. So you already know, you already see that you can make B learnable, right? It's super simple, right? So you could also make H0 also as a learnable parameter, and in some cases it would also improve the results. So that is also a neat trick to do. So here would add then the B, self B. Okay, so now we have the gates. So the gates, let's just make clear what the gates will produce for us. So the gates shape will be the batch, of course, and then what will be the next one? The hidden state times 4. So 4 times hidden state. That is what we get from the gate. Then we can calculate these gates as in the equation. So input gate at point t, at time step t. So it's a torch of sigmoid. I think in the Phased-LSTM paper they did not so nice thing that they used the for the 10H also the sigmoid sign, but I'm not sure, like, is there any other sign for 10H, so that maybe you can just type in 10H in the equation, that would be more clear. So gates over the batch dimension, copy everything, and over this hidden dimension, remember we have 4 times the hidden size, so we need to split it in 4 parts. So again, the Pythonic way of accessing the arrays, very simple, very useful, you know. You just have self hidden state, hidden size. Very easy way to select out only that part that is interesting for us. And the AutoGrad takes care of everything. It will keep track of the gradient between all of these selections. So here, again, I think this is like much nicer way how to operate than in TensorFlow, like without the eager execution, where you would need to prepare all of this in advance with the, I think it was called scan operations or something like that. So here, you would then collect it by the second part for getGate. For getGate here. Okay, that means that this initialization of the for getGate should happen basically in the range of this one. So I will add maybe in this to-do comment here that you could initialize it in this range by 1, and that would be beneficial. So if you think about the sigmoid, basically it will open the gate if we initialize it in that way. So this is here. Then the output gate, O. Output gate, again, the next one from 2 to 3. And finally, the cell gate, so the CET, so, right. So the cell gate is from 3 to 4. Or, of course, you could simplify these lines a little bit, but I want to make them uniform. So like that. So I will make a small pause, maybe, so you can catch up. So if somebody is missing something, please let me know. So if somebody is ready to move on, also let me know, a chat or some other place. Meanwhile, I will try to find where is my microphone so I can mute it a little bit. I will just give, let's say, a few minutes and then we'll move on. Thank you for feedback. I see that at least 2 people gave me pluses and ready signs in the chat. Really helpful if you communicate. Oh, okay, where is the mistake? Yes, thank you, thank you. Walters is great with spotting mistakes. Thank you, really good. That's why I like working with smart people. So okay, 10H here, also a mistake. If you look at the equation, 10H there is. So then the next one is C, torch sigmoid. So this will update the like the equation is sometimes written in one line, but I like to split it in 2 parts. So for the cell state update, so FT times C plus E. So by the way, these are the Hammond products, pairwise multiplications, not dot products. Okay, that's cool. So from that equation, then the H, torch 10H, and from the CT multiplied by the output gate, how much we want to let the signal come out of the cell. And then we add the signals to the H out. So because we are developing our own architecture, I'm not tracking actually the C state here. From the other point of view, if I would like to pass it back, then I would need to track it. So anyway, if you would like to use this for the rollout purposes, so that you would not give HC as none, then you also would need to track not only H out as a list, but also C as a list, because otherwise you would not be able to keep rolling the next cell state without those two vectors. But still, like for our purposes, it's not needed, so not spend time on collecting C's. So here, let's write this T out, just like a TH out maybe. I don't know, like tensor H state out, whatever. So torch stack of H outs. And then the last thing is that the next operations in our function graph probably wants to work like a normal, like the batch is in the front. So we should get back the batch in the front. So I will also change this one. So T out, TH permute, so the 1, 0, 2 to get the batch in the front like it was. So that's it for the vanilla version, basically. So let's see if it works. Also, by the way, to actually train it fully, you can just copy all of this stuff into Google Colab, and it should immediately work. I will also do that in a second. So sorry, I'm just like run it in the background to see that there is no bugs. Hopefully there is no bugs. So I will also wait a little bit. So yeah, let me know that you're ready, and then we'll launch this in Google Colab. Okay, it's working for me. So and you can also try to launch it in Google Colab yourself right now, and we'll add also the Peep Holes, right, and then we'll move to the Phased-LSTM implementation. So yeah, let me know if it's running for you, and I will also make a little pause now. Again, thank you for interaction. I see at least 2 people saying that you're ready. Hopefully others also will manage to do that. Yeah, meanwhile, I will still keep open this code here so others can catch up, and I will run maybe, so what should I do? So maybe you can take a screenshot, or I will just return back to this in a second. I just want to show you how it works also in Google Colab. So if you go to the Google Colab that you can log in with your Google account and create these Jupyter notebooks. With these notebooks, the great thing is that you can also access the GPU and TPU for free, of course. So that's great. And also you can have the funny animals running around. So there was some kind of way how you can enable those. So here in the runtime, so you go into runtime, and the change runtime type to the GPU. So the only thing that you cannot do here is to mine for the crypto. If you do that, they will ban you. And I don't know, like they probably have a really good protection of that. Somebody knows how they do this interesting topic. So then, if I copy in all of our code just in one cell, and I run it, and look at the nice cats going around here, it will copy the dataset first, if I remember correctly. So the MNIST dataset, and then it will detect that there is GPU available first of all, and it will include the whole dataset then and run it on GPU. So that should be a little bit beneficial, and we'll see how good it works. So you can try that yourself. Just copy this in the Google Colab, choose to have the GPU and run it. And in a second I will return to the code, so if somebody didn't catch the last part. Meanwhile, it's still training, and then we'll move to these peep holes. So we'll implement the peep holes, and I suspect that the actual Phased-LSTM implementation based on the same code that we just did, we will do the next time probably, but you could also you already know how to do these the basic skeleton. So I think that most of you should be able to also implement Phased-LSTM yourself now, but still we'll do this together also. So the one thing that's missing here is the peep holes. So while it's training on the Google Colab, for me already in the second epoch for the 3-class scenario, I get 96% accuracy. So if I show you this, so the correct way how to approach next is to actually increase the difficulty of the task. So as you remember, you can increase the difficulty of the task by adding more classes, for example, or like changing the sequence length from the 28 time steps to over 700 time steps. So just by changing the way how you feed the data. So there are multiple ways how to increase the difficulty and break the LSTM, so we can see the benefits of all the things that we can add. Okay, so for the beginning part, we can start breaking some of this. So I'm not sure like what exactly will constitute to the worst performance, but I suspect longer dimensions. But let's start by adding just all of the classes. So 1, 2, 3. So maybe I don't like doing that. So this is the MP. So MP range 10 to list. So now I have all 10 classes included. All 10 classes included. So if the code is correct and I run it, then I should see a little bit degraded performance, hopefully. And then that would be a good like benchmark for adding more features. Okay, also it will work a lot slower because now we have at least like 3 times more data points. So that is what we have there. Okay, let's move on to the Peephole. So if you look here, so in this implementation, we have 3 places of multiplication with this one. So I'm just thinking how to do this more efficient. So we'll need to split the gate. Sorry for coughing. Really sorry for that. I don't have COVID, hopefully. So because I have some other issues a little bit. So here we have Hammond products and learnable. Basically, this seems like just a learnable vector. And we also have that we need to split the gates actually in in some for the C gate. We will need to split it because of course the peep hole for the C doesn't make sense at all. And also we can see that the C is actually not so here's the t minus 1, and here's the ct. So that means, again, we'll need to split gates even more. Let's look how it looks like here. The C goes here, the C. So in this schema, if you don't have the equations, then it's misleading, because it seems like that CT is going inside the input and output gates, but if you look at the equations, then in input gate, it's a C mean T minus 1. So, but that actually would not be really the... So it's interesting. I'm not sure about that. So we can try out as a T minus 1 or just T. Maybe that is a mistake here. I'm not really sure. So they say that, I'm not sure like from which paper they take these peepholes from here, from the 11th paper here. We can double check that a little bit later. So just implement that, and I will double check if it's actually CT in all of these places. If somebody else double check, please let me know in the chat, so that, because it seems strange a little bit. So if we go back to the code, that should be not so hard. So we need a extra learnable vector. So what we can do is to add the extra learnable vector here. So self, this will be the peep. So w peep. Maybe so this is a vector, so let's keep it with the small letter. Yeah, so like that. So, and this one will be, so if it's if it is a Hammond product there, maybe it would be, no, I'm not really sure. So we can add it as a uniform. So need to learn. Yeah, not sure really. What should we initialize it? So if you have ideas, what should we? So I think once could work probably. I'm not sure about uniform. So we can try out and then change it. What would be the best initialization for the peep holes? So we have three places where we have those. So the gates are here. So we'll need to start splitting the gates, unfortunately. Let me look at the equation. For input gate, for get gate, and for output gate, everything's fine. So input, for get, output. And it's great that those are the first three ones. So the first three ones are good. So we can split it out here using xt by repeating 3 times, not 4 times. So we will repeat it 3 times, not 4 times. Then this one we also repeat it 3 times, and then we'll select this part also just for the first 3 parts. So again, the colon, and then the hidden size times 3, and with this one with the U. And also here we'll need to select this one. Okay, but only like that. Great. And we'll add these peep holes, but of course there's the issue with regards to C or CT. Maybe it will not be exactly the same implementation, so you can fix that a little bit later. I will also look at the original paper, but basically the idea is that you would try to add them here. I will use the previous C for that. So here we can add the other one. So the peep, this one, multiplied by the C, so the C from the previous state, repeat by 1 by 3, just a pairwise multiplication. So these gates are good. These gates are good. Then what about the CT? CT don't have the that port, so we need to actually have that multiplication as a separate part. So we can copy probably the first part of the gates. Just so that we don't need to change the code. We can copy also this part and give it only for the last section. Then also the same fragment should be used here, and this without repeat, of course, because now we have only one fragment of this whole thing. So here and here without the batch dimension here, I guess. Actually, that is not batch dimension, the input dimension. So, like that. I think the peep holes in like a very rudimentary way is done. So I will just check it a little bit more. So, not sure about that CT-1 or CT. Need to double check with the reference paper, so I will do that for the next time as well. And next time we'll complete this with the complete Phased-LSTM. Now you already get a sense how to I'll do all of those connections in the equations. So I will copy this part. First of all, I will try to run it, of course. So and then I will also show it a little bit up and down, so you can catch up. I will maybe also give my code as a finished one. So yeah, I will add that when this is working. I will post it in chat and also add to the video. And so there are a lot of things that you can experiment yourself as well. I already added those to do comments. And we'll do interesting things next time as well. So what is here? What is here? There is a bug. Maybe Walter can help me quickly find it. So what is the bug? This is the, so this part, the C. Here it's hidden times 4. In here is hidden times 4, so that's good. So the good news about the PyTorch, we can add the breakpoint. That is something we can like debug it in the middle of the function graph. We will quickly find what is the problem. Because I specifically split it in not in 4 but now in 3. So 3 parts, and using those 3 parts together. So I hope that it should work like that. Okay, why it's taking so long? Hello. Maybe I need to restart it. I always have the temptation to restart it. Oh no, the breakpoint didn't work. Why? So, okay, let's add another breakpoint here. Try again. Maybe somebody else can fix it faster than me. I will check the chat. No ideas. Just a second. So it's working slowly. Why the breakpoint not firing? Okay, yes. So, and then we go, no, just skip the part that I wanted. Oh no, kind of don't know how to do the breakpoint correctly. So I'll do something like that. Now it will work. Again. We'll find the problem. Somebody with a faster computer can find the problem faster than me. Meanwhile, I can look what we had with the Google Colab. Google Colab. Actually, after the 6th epoch with all 10 samples, I get also, so let me share the Google Colab. So after the 7th epoch, I get 97% accuracy. So, but the curve is not so steep as before, so that's good. So at least we have some reference, basically, so we can compare with the Phased-LSTM later, and with the Peep Holes as well, of course. So now it braked in the right position. So, and the way how I would self hidden. Ah, interesting. Hmm, you might be right. Let me, yeah, so of course, like the input, so this is not the batch actually. You're right, that is the input dimension like that. But then I'm also thinking about the output dimension. So if it's like 3 times in this place, I think it should be also the 3 times of the output. So I don't want to have them multiplied in the middle part. So let's add like this. So the selection also for the output. So let's see if that works. So I'm running it, and then also here I have the same bug. So here as well, the same bug. But let's see if it fails here or some other place. Oh man, it takes so long. Okay, so now it failed at hopefully the other position. So yeah, great. So the problem was that I was looking at the matrix and I was thinking that it contains the batch dimension as well, but actually it contains the input dimension times the output dimension. And of course we need to select out only that part. And if you run it again, then hopefully it will work. So I think it should work. So I will start copying the code in the, oh no, it didn't work. So just a second. What didn't like here? Oh, okay, I unfortunately messed up something with the, okay, what did I mess up? From the 3 to the 4, from the 3 to the 4, from the 3 to the 4, the size of the 16 by 0, 16 by 0, how that's possible? 16 by 0, 16 by 128, 128, h vector, that is fine, the x vector, so interesting. So I will add the breakpoint, maybe Walter has already fixed this, if not, maybe, so I will try to fix it. So this is basically the same equation as before, just for the only the last part of the gates, for the C gate, for the cell gate. And in this part we don't use the peep hole because it doesn't make sense. From other side, if it's C minus T minus 1, maybe it makes sense. So okay, again, it don't make the breakpoint in the right position, unfortunately. So just a second. Just a second. This is the last bug, hopefully, before making this peephole architecture work. And that will be the architecture that will modify the next time. So here, what is the problem? Let's start by splitting the first equation. The first equation works. That's good. Good. If you look at the size of the first equation, 16 by 128 looks good. The second part of the equation, size looks good. The last part of the equation, size, okay, but that should not be a problem. Because, oh no, but that is problem. Okay, why this is a problem? So the bias, But hmm. Okay, let me check this one. Size. Oh yeah, you're right. Okay, that's not problem because we can. So what we can do is you that's good observation. So we can just have this as a gate c as another just another variable, and don't use the previous variable, and then just use this here as a gate c with a 10h, and it should be fine then. So if I run it again. Yeah, and I will prepare some of the materials for the next time as well, where you will see some very interesting hacks, like for example adding layer norms for the projections. It really helps to increase the performance of the LSTMs. And also we'll add these phased LSTM gates, and that's going to be great. So yeah, it works. So thank you, Walters, for saving me multiple times today. Yeah, so for example here we need a specific new variable for the gate, and here we have the all three gates of the those together. So the only question here that is not really answered is this like, so the question is this should this be CT or CT minus 1? So I will check that in the reference paper. So if it's a CT and CT minus 1, then you'll need to split this equation even more, but you already know how to do this. So just summarize for today. So if we copy all of this code, and I will share this also shortly, and go to the Jamboard. First of all, we get quite good results with the vanilla, but if we add the Peepholes, we should get even better results, hopefully. So it will not be that quick, probably. So if I copy it here, run it. So it's running. So it will be fun if actually these Peepholes would degrade the performance. Then maybe we have some kind of bug with the idea of that CT minus 1, but still. So yeah, let me know how it works for you. Meanwhile, while this is running right now, I will scroll back to the code so you can copy it a little bit, and I will also add this to the right now to the Google Drive and share the link for you. So if somebody had problems following it and somebody wants to look at the code that I have, you will have that opportunity just in a moment. And the next time we'll complete the paper that I presented you in the beginning with all of those extra gates for the phased LSTM. And also I really want to show you these cool things that we discovered also with ASIA and some other research projects, where you can have all those hacks that you can add for the LSTM to improve the performance. So that's about it for today. Hopefully it was fun. Finished. Next, so the last thing missing for the fun is the fun dataset. So next time we'll use the Kaggle dataset for the accelerometer detection of if the person is standing or sitting or something like that. I not exactly remember what was the labels. And so it's a high frequency accelerometer data, and that will be more fun than just using the MNIST, but still this is interesting. So I'm adding the finished one here. So I added the finished one in the so I added the finished version inside the chat window. Yeah, so let me know if you have some comments, questions, ideas for the next time. And I think in general that's it for today. Next time we'll work on the Phased-LSTM and those hacks that I mentioned. Hopefully you will see that LSTM is actually quite powerful model. And yeah, the last thing, if we go back to the Jamboard here, so with the Peep connections we see immediately a very significant improvement. After the second epoch, immediately we get 96%, 94%. That was what we get before after the sixth epoch. So again, if we get the very high performance after 2 epochs, we need to increase the difficulty of the task and then see what we can get. So yeah, that's it for today. Hopefully you liked it. Hopefully next time also will be fun, and meet next time, right?